I'm in the process of creating a series of video tutorials for doing elementary structure analysis problems using the 3D Experience platform. Now, I noticed that some of these tutorials are also useful to be done in the Catiav5 program for the sake of the people in that community. Uh, I already did tutorial one, which uses a particular strategy that you would like to, if you wish, you can watch it. However, I'm going to do a different strategy in this current tutorial. The problem is going to be the same though. Please keep in mind that TIA is not very user friendly when it comes to beam elements. In other words, maybe a civil engineer is better off using, for example, the ETAPS program or the SAP program. But anyway, if you insist as a mechanical engineer or as a civil engineer to do the problem with a CATIA, here is how it's going to go. The problem that we're looking at involves an internal hinge. So we have a statically determined structure here, which is subjected to these forces and moment. And then there is an internal hinge here, which I'll show you how to model it in the CATIA program. I call these things not the rocket science series because there's nothing advanced in it. It's just I'll show you the process of doing it in CATIA. And also, as I mentioned, there are programs that are more amenable to beam elements such as SAP and ETAPS. That's why I call this thing killing a fly with a cannon type problem. Okay, so this problem is actually taken out of Hebler's structural analysis book. And notice that the cross section is not specified, it's only that the bending second moment of area or I about the bending axis is given. Doesn't matter what shape it is. And the Young's modulus is 29,000 KSI. Okay, the dimensions are given here. If if one decides to go and calculate the deflection, vertical deflection, it can be done very easily using the principle of virtual work. Since I've already talked about this thing in the tutorial one, later on I'm going to show you the 4 slides that are associated with doing the virtual work calculation for finding the transverse deflection of the point B. I'm not going to talk about it, but I'm just going to show you the slides. Now the strategy is going to be as follows. To do it in CATIA, I'm going to create 3 lines, left line, middle line, right line. So this is 12 feet, 12 feet, and 15 feet. And in tutorial one, I joined left line and middle line because I don't want to have a duplicate node between the two of them. So when you join it and you mesh it, there won't be any duplicate node. However, you can still put a transverse force of 8,000 K at that location. In this particular tutorial, I'm not going to join these things. So what I will do is create a analysis connection between these two vertices and between these two vertices. When it comes to the first connection, I'm going to declare it as rigid, and all degrees of freedom are being transformed from one end to the other one. When it comes to this other connection, rigid connection, I will release the rotational degree of freedom about the bending axis. So that's the main difference. I will not use join, but I will use a connection here, rigid connection here, and a rigid connection here, which was already done. And once we do that, then of course we're going to apply the load and restraints, and we're going to run it. Okay, so here are the 3 slides from the tutorial one. It's repeated for your convenience. Real structure, virtual structure, and the virtual work for beams. The final value should be roughly 4.58 downward. So let's go ahead and do that. Let me start with the part file. And notice that contrary to tutorial one, that I did this thing in generative shape design because I needed access to join. I'm not going to join just to convince you. I'm going to switch to part design so that we don't have the join option. Okay, let's create our 3 lines. So a line, point and direction. The point start at 0, create a point coordinate 0, 0, 0, which is created right here, direction y, and the length is going to be 12 feet. 12 feet. Okay. So there we are. That's the first line. I'm going to do another one. Same method. The point is here, and the length is 12 feet. Direction is y. Very good. So the second line. Third one is going to be, point is going to be there. This is going to be 15 feet, which means 180 inches, and direction is also y. Okay, so I've created all my lines here. Let me also create a point of this line, of these lines, which will be used for as a coordinate, as a orientation geometry item. So click a point, and I'm just gonna not, it cannot be on that line. So let me change the value of x so that, for example, it's off the line somewhere there. Okay, very good. The actual number doesn't matter. Good. Now, let's apply material. So we're going to apply material to this. If I can find it right here, apply material, metal, steel on that part, and double click on steel. The only thing that I have to do is slightly change the value of the Young's modulus from 2.901 in the database to 2.90. But these things are not used for being problems, so we say okay. All right. Now we're going to go to analysis and simulation, generative structure analysis. We're doing a static problem. Okay. So we have 3 lines here. We're going to mesh them independently. So we click on this beam element. This one, I'll make it 1 foot long each, so 12 inches, 1 foot. So there's going to be 12 elements there. And do another one right there, same 12 inches or 1 foot. And then another one here, also 12 inches or 1 foot. So there's going to be 15 elements on that. Okay. So if you actually looked at this, right click mesh, mesh visualization, what's going to happen is that you see this is the left line, and if you travel down this left line, you see the right node 11, 12, 13, and then suddenly 15 becomes 15. Oh, hang in there. So we go, here is right node is node number 1. Zoom in, right there, node number 1. But when you go on this side, it becomes node number 15. That's because there's a gap here. When we join it, these two essentially will be merged together, but not here because we're not joining it. And the same thing on this side. There's going to be duplicate nodes from when you approach it from the right and from the left of these 2 lines on the right side. Okay, let's do the 1D property. Click on it. Actually, let me deactivate this. Okay, so 1D property, I'm going to select this support. Notice that it creates a local coordinate system, but I want these things to be aligned with that. In order to do that for the orientation, see that orientation geometry? I select this point. Notice that when you do that, it kind of turns these things around so that this Z becomes lines up. One of these coordinates become parallel. Okay, how about that? Let's try it. Just watch the yellows, the red stuff here. See, it turned it. Okay, so that this y is parallel to that x, local z is parallel to local z, and local x is of course parallel to global y. Well, that's okay. Now you click on the wrench here, and you know that the cross-sectional area about the bending moment, these x, y, z are referring to the local coordinate system. So the bending direction is y. So I put down 30 inch to the 4. And because my units are set into meter, it converts it into that. Okay. So that's correct. And then say, okay, do the same thing for the next one. Oh, no, no, cancel. We already did that. Do the same thing for the next line, which is over here. And for orientation, select that same point. It tilts this thing. Click on the wrench. These are the correct values because they all have the same cross section. I don't have to type it in inch to the 4 again. You're going to get the same number. Let's say OK. And finally, the last line. Orientation geometry, that point. Okay. Click on the wrench. These are the same numbers as before. We don't need the cross-sectional area because we're not considering the axial deformation. Okay, good. If axial deformation was important, you just add the proper A, which has to be given to you, and then proceed. Now we're going to create our connection. So let me hide these properties here. I don't want to be able to cancel. Hide them. Good, good. So, connection analysis supports are here. This is the general analysis connection. So what I'm going to do is I'm going to hide this. So that's the first one between this point. For the second component, I select that end. Okay. And just to show you what has happened here, we have created one connection here. Later on, we're going to declare this thing as rigid. Then we do another connection between these two vertices. Let me hide this so that you can see what's going on. So the first component right there. For the second component, the other end. I'm going to bring this thing into show mode. Okay, right there. So we have created, this one is over here, which is all degrees of freedom transferred. This one is the one that rotation about the bending axis is released. Okay, so let's see now, where do we do distance connection? There's the distance connection toolbar, and here's the rigid connection property. Let's start with the first one. Notice that transmitted degrees of freedom, all of them are transmitted, okay, which is good. That's what you want. Okay, I don't have to do that. This is by default, all of them. Very good. Now for the other fellow, that guy, the second one, transmitted degrees of freedom, we don't want rotation about the global x direction to be transmitted. That's what an internal hinge. So rotation about the one direction. Notice that this is global. Okay, and then we say fine. Good, good. Now let's apply restraints. So this end is clamped. Very good. This end is on a roller support. So click on the user define. Check that. So this point, it can move in the direction Y if it wants to, global direction Y, which is free the translation to. But it can rotate about global direction X. Okay. It cannot move in X. It cannot move in Z. Okay, very good. And of course, these two rotations prevent out of plane and torquing, motion. So we say fine. Hopefully, I didn't make a mistake here, but let's check this thing one more time. This point cannot go in the direction Z and X. That's good. It cannot rotate about direction Z and direction Y. That's good. Good. Now let us put our load. So load on this uh, uh, location, and the value is 8,000 minus 8,000 pound downward. See that? Minus 8K, 8,000 downward, and then a moment like that, 30K feet, 30K means 30,000 pound feet. Okay, so this is fine. And then we're going to do a rotation, not a rotation, a moment on that point, and the direction is correct right there, and this value is 36,000 pound inch. Remember, 360,000 pound inch. Now remember, what we had here was 30,000 pound feet, but because my unit is in inches, even if I type 30,000 pound force feed, it'll convert it to this, which is my default unit. Okay, very good. So hopefully we haven't forgotten anything. Let's run it. And lo and behold, we're going to get the same answers that we got before. 4.58 inch displacement downward. So let's go ahead and plot the reflection of 4.58. You can see that if you look at this thing from the side, first of all, let me change it to average ISO and look at the view from the front. And notice that you have a kink here because this was a internal hinge, and this one was okay. In the tutorial one, I joined these things. Here I created a rigid connection between the ends of the two pieces. So this is tutorial 2, and then there will be a follow-up tutorial 3, which uses a different strategy. All right, folks, see you later.